about isospectral manifolds. Orders in quaternion algebras.
Yeah, thank you. So, I mean, first of all, many thanks to the organizers, Eric and Magnus, for putting together a very stimulating workshop. And thanks to all of you for coming. It's 9:30 on a Friday after an intense 4 days. So, yeah, it's great. And thirdly, everything I'm going to say is joint work with Aurel Page in Bordeaux. So, I'm going to open the workshop with the question, can you hear the shape of a drum? And I'm going to devote the entire hour on the last day of the workshop to that question. So this was a famous question Katz asked in the 60s. Now, to address the question, we should turn it into a question. So let's actually spell out what it means mathematically. So first of all, for me, manifold will always mean compact, connected, oriented, Riemannian, and without boundary. A small print is that sometimes it will also actually mean an orbifold secretly. Yeah, too much about that. Except that, you know, when we talk about homology and differential forms, you have to take them in the orbifold sense. Okay, and actually, I should say, the orbifolds that will appear are actually very nice, and this is a technical. They have a finite global covering by a manifold, and most things you can do upstairs on the manifold. Okay, so let's turn Katz's question into a mathematical question. So if you have a manifold, the adjectives above, then in every degree I, you have a second degree differential operator, the Laplace operator, acting on the space of differential I forms. So I equals 0 corresponds to functions. And it has a discrete real spectrum. And so the question is, so we say that two manifolds are isospectral if in degree I, the two spectra, two manifolds just agree as multisets. Literally, the numbers are the same. And so, zero isospectral is abbreviated to isospectral. So on function, the spectra on functions. And so, yeah, the original question can be phrased as, do there exist, so this is the contrapositive, I guess, do there exist manifolds on which the Laplace operator has the same spectrum, but that look different? They sound the same, but they look different. When I told my wife, who's not a mathematician by any stretch of imagination, that I was working on this type of question, she got really excited. You know, oh, can you hear the shape of a drum? She's into music, so she thought she knew exactly what I was talking about. And then I said that we are currently particularly excited about hyperbolic three manifolds without boundary. And I think that was the last straw where she gave up hope that she could ever think about anything like this. Oh, and one more thing I should have said. So this is very fresh, very hot off the press. It's not on the archive yet, but Aurel and I rushed to make it human readable. So it's not archive ready. It'll need another sort of polishing pass, but it's on my website. You can check all the details. Of course, you're also welcome to ask me about details. Okay, so this is the original question. Now, perhaps, and in fact, it turns out it'll be a bit more interesting to soup it up a bit and imagine that we have unbelievably good hearing. We can hear not just the manifold, but also some sorts of vector bundles on it. So we say that, yeah, can you find, maybe I should have said actually to the original question, the answer is there do exist manifolds like this. So if that's all you cared about, you can pack up and go home, but of course we don't operate that way. So the next question is, okay, can you find manifolds that look different, but on which the spectrum of Laplace agrees in all degrees? And again, the question is, yes, you can. So you cannot hear the shape of a drum, even if your hearing is absolutely phenomenal. So, okay, well, again, we don't, such a yes, no question. That was never the spirit of the question to begin with. Really, I guess, at this point, you become a bit desperate. Okay, so what properties of manifolds can we hear? Surely that's what Katz had in mind. all along. So we can't hear the full shape, like everything, but we can hear some things. So if two manifolds are isospectral in all degrees I, then they have the same dimension. They have the same volume. Remember, my manifolds are. They have the same Betti numbers. So the dimension of homology is the same, but I really like the next one. You can't hear the cohomology ring, the real coefficients. You can hear the graded vector space, but you can't hear the ring structure. That's quite neat. And perhaps again related, you also can't hear the p torsion or the p primary torsion for any prime p. So for any prime p, you can pick one, and I can create a pair of manifolds that look different. Sorry, not just look different, but they look topologically very different. They have different p Celoff torsion subgroups in the first homology, but that sound the same. So for dimensions 4 and higher, this can be deduced from, although Sonada didn't spell it out, but it can be deduced from work of Sonada. But his technique breaks down in dimension 3, and in that case, it's a result of Aurel and mine. But that's not what I'm going to talk about today. So, to earn the right to speak at this workshop, one has to make a connection between.
So, sorry, can I ask a
Yes.
to go back? What does it mean they have the same dimension? Because, I mean, spectrum are sort of organized differently in different dimensions.
No, so this is just saying that the homology groups have the same dimension.
Oh, okay.
Were you referring to? Oh, sorry, the manifolds.
The first point.
Yeah, the manifolds. So, I mean, we didn't specify. A three-dimensional manifold cannot sound the same as a four-dimensional manifold if you can hear
But the
spectra in all degrees.
differently. That's what I'm basically trying to ask.
So you have to know, yeah, I'm not considering the full multiset of all eigenvalues in all degrees at once, but if in every degree,
If two forms sounds the same, then dimensions is the same. That's a statement.
if the manifold, if the I forms sound the same for all I mean, it's kind of obvious because, when one manifold is high dimensional, then you'll have a space that is empty and another one that isn't.
But this is true for functions, right? I mean, just the function spectra, if they're the same, then they have the same dimension. No?
Is that true?
Just by the Weil law. I mean, that's
By the Weil law. You're right. You're right. Yes, thank you. Right, so I'm supposed to draw parallels or connections to number theory. So here it goes. So you can organize we fix a degree I, and then you can organize these eigenvalues into a generating function, which is called the spectral zeta function, spectral zeta function of the manifold. And just from formal properties of the Dirichlet series, two manifolds are isospectral if and only if they have the same zeta functions. Now, however, the parallel goes even further. So this is very well known, and actually, yeah, well, I'll come back to that. The parallel goes further, namely, like zeta functions of number fields, these zeta functions have a special value formula, and I alluded to that in the first talk already. So I'm not going to state the actual formula. I have an easier time, otherwise I would have to talk about regularized determinants and so on, but I just need to compare two manifolds. So I'm just going to give you a consequence of the Jaeger-Miller theorem. And that says that if two manifolds are isospectral for all I, then they share a certain expression, and the expression is an alternating product over all degrees of, in degree I, you take the ith regulator divided by the size of torsion homology in degree I. And what is this regulator? That is sort of like a regulator of a number field. It's the co-volume of integral homology inside real homology with respect to a certain canonical pairing. You use the Hodge-Star operator, which we've also seen in the course of the week, to cook up a pairing. So these regulators, if if the ith homology is zero-dimensional, then these are determinants of empty matrices, so they're one. But otherwise, we expect them to be transcendental numbers. On the other hand, of course, the torsion, these are just integers. And okay, so an explicit case of these regulators that you already know is if you unpack the definitions in top degree D, you'll find that this is nothing but the square root of the volume of the manifold. Any questions up to now?
What volume form are you using on HIMR?
So you have to fit, I mean, my manifold comes with a Riemannian structure. So,
Yes.
and it's oriented, so I have a volume form. But you're asking about the definition of this pairing, or?
You're asking about, the definition of the volume of that, like,
Yeah, so you have to, there is a certain canonical pairing defined on this, and you take like the determinant of the gram matrix of that pairing with respect to your basis. Yeah. Any other questions? Okay. Now, let's inspect this formula a little bit. So we have a bunch of transcendental numbers and a bunch of integers. And remember, my manifolds are oriented. Now we have Poincare duality, and if you trace through the definition of these regulators, you'll find that it sort of pairs up regulators in degree I and d minus I, but with an inversion. So the ith regulator is the inverse of the d minus ith regulator. And so, let's go back to the formula, the Giga-Miller formula. So combine it with Poincare duality, you find that if d is odd, then you have these ith regulators and d minus ith regulators, they combine together, you pick up squares. And then I keep harping on about this, that the regulators were the only entities in that formula that are transcendental. And the rest were just integers. So you deduce that this alternating product, when you go to half the degree, but with a square, is rational. And this is supposed to be almost impossible, right? If a bunch of transcendental numbers whose quotient or whose product is rational, that really demands some sort of strong explanation. Now I've explained it using the Giga-Miller formula, but we'll come back to this. On the other hand, when d is even, then Giga-Miller tells us nothing because the regulators in degree I and d minus I cancel each other out. I guess this is my version of the double slit experiment. Okay, so some natural questions. First of all, are these regulator quotients rational in each degree I separately? In the Giga-Miller formula, there is no such formula in a single degree. It only gives you this whole package of all degrees at once. And so this is even, still assuming isospectrality for all I. What if I assume isospectrality only for my favorite I? Is the regulator quotient in that degree rational? So these seem to me like very natural questions, and I don't know the answer in this generality. So if you just give me completely arbitrary isospectral manifolds, I don't know. There are very kind of strange ad hoc constructions of these things. But I want to stress that when you ask about each degree separately, so you don't even assume isospectrality outside of your favorite degree, the Giga-Miller formula suggests nothing. It only comes off the ground if you have isospectrality for all I. So this is perhaps a very optimistic question, but I don't know. And if the answers are positive, then, okay, now we have some rational numbers. What are they? Which primes can appear? What do the periodic valuations at the different primes tell you about the manifolds? Now, I said I don't know the answer in general, but I do know something, and that's what I'll tell you today. There are two major constructions of pairs of isospectral manifolds. Some people will say there are more, And some people will actually say there are less, but we might get to discussing this in a minute. One is due to Sonada, and by the way, I'm presenting them in reverse chronological order, but in order of decreasing fame, I think. Sonada's construction is the most famous one, using representation theory of finite groups. And he was led by the analogy with number fields that we saw. You have these zeta functions, and the question of whether there exist number fields with the same zeta function, but that are not isomorphic, was well known and actually is completely understood in number theory. And so he imported the construction from number theory of number fields with the same zeta function to produce manifolds with the same zeta function. And the other construction is due to Vignerat, and that's essentially an automorphic construction. It uses automorphic forms. And that's quite a bit more complicated, but also it's less well understood in the sense that Sonada gives you a recipe, and if your scales are correct and you've measured all the quantities correctly and mixed them in the order that Sonada tells you, you will get a pair of manifolds that are isospectral for all I. There's a warranty, you can turn in the product if something doesn't work out. Vignerat is more complicated. It says that sometimes, she tells you what to do, and then sometimes with some extra assumptions, which are not very well understood, the manifolds will be isospectral. And it's these extra assumptions that we want to inspect today. So let me sketch Vignerat's construction to you, at least well, I think what I'm sketching is basically what people say is Vignerat's construction, but if you think about it carefully, what she does is vastly more general, and I will stick to a special case. So take a number field, take a quaternion algebra over that number field, and assume it's not totally definite, otherwise you'll get just single points rather than proper drums. And then I would agree with my wife that it's too far. And take two maximal orders in your quaternion algebra. Now, it's a strange fact about the arithmetic of quaternion algebras that you can find maximal orders that are not conjugate. And that will be the interesting case. Then the multiplicative group of the algebra, and therefore of these orders, naturally acts on an associated symmetric space. And we are going to take quotients, but we want those quotients to be oriented. So for simplicity, well, actually, no, not for simplicity, but to ensure that we get something oriented, take elements of positive reduced norm. Whatever, I mean, if you haven't done much with quaternion algebras, then just ignore this. And then take the quotients of the symmetric space by these two discrete groups. And we saw examples of this throughout the workshop. These are these arithmetic discrete subgroups that appeared in Amina's talk and then kept appearing. And then Vignerat says that sometimes these manifolds will be isospectral. So let me explain. Sometimes means there is only one known sufficient criterion so far. And this is a theory. So I'm stating a combined effort of many people. I mean, Vignerat had a theorem, and then her criterion was reformulated, etc., etc. So the condition that ensures this is not necessary, it's sufficient, ensures isospectrality is called non-selectivity. And the simplest version of it is the following. You want for every conjugacy class in the unit group of the quaternion algebra, you want gamma 1 to intersect that conjugacy class if and only if gamma 2 intersects it.
Yes, that actually is similar to what Sonata does. There is a similar condition over there as well.
This is yes. So that's why some people say that there is only one construction. But I'm going to dispute that claim.
All right.
Indeed, this makes it look like Sonata's and Vignerat's constructions are special cases of one and the same thing. Yeah, thank you for that remark. That's everybody processed this condition. So for every conjugacy class, either both maximal orders, well, unit groups intersected or neither does. That's called non-selectivity, and no conjugacy class selects between these two. And in that case, the manifolds are isospectral for all I even, which is also true in Sonada's case. Okay, now in fact, this non-selectivity condition implies something even stronger, with something that is called representation equivalence. So now it's going to get a little bit more automorphic and a bit more technical, but bear with me. So take the following group. You look at the points of D over all the Archimedean completions of your field. So this is going to be like GL2Rs and GL2Cs, and also some Hamilton quaternion things. So I'm taking the unit group this and the product. Then these L2 spaces, so you take these bunch of GL2Rs and GL2Cs, modulo gamma 1 and modulo the center, and modulo gamma 2. These are both unitary representations of this group G infinity. And we say that the groups are representation equivalent if these are isomorphic unitary representations. And actually the theorem of, so you will notice that I think compared to the previous slide, 2 names are missing here, is that under this non-selectivity condition, gamma 1 and gamma 2 are representation equivalent. And the other 2 people proved using the trace formula that representation equivalence implies isospectrality for all I. And so this, for example, this criterion was used by Voigt-Linowitz in a very exhaustive search of pairs of arithmetic groups and checking which ones are representation equivalent, which ones aren't. And the smallest volume of isospectral manifolds, orbifolds, they found had this volume. You don't need to remember this number because I've got it hidden on a blackboard that I'm going to reveal in it. Okay, so to get what Aurel and I do off the ground, I'm going to massage this construction a little bit and reformulate it slightly adelically. I wasn't sure if I was allowed to use Adels when there are actual just topologists in the audience, but decision was taken off my hands yesterday, so now I feel free. No, but basically you can think of this simply as the product of all completions of Q. This is not quite true, but this will be good enough because we are only going to care about the Archimedean completions. So these will be a bunch of reals and complex numbers. Although, yeah, okay, here I have so these are completions at the finite places. So a bunch of p-adic fields. And again, I'm going to take the elements of positive reduced norm. And I'm going to take a maximal compact subgroup of this group G infinity. So we said G infinity is something like a bunch of GL2Rs and GL2Cs. So this is something like this K infinity is something like a bunch of orthogonal groups and a bunch of unitary groups. And we have the center again. And we take some nice compact open subgroup of this thing. Think just products of GL2 over ZPs, various primes P. And we're going to form the following double quotient. So we have this, this adelic thing on the left, the global points on the right, and on the left and on the right, we have these compact subgroups. Now, this space, G infinity modulo the center and modulo K infinity, that is the symmetric space that I alluded to. So GL2R modulo orthogonal group is basically upper half space, and well, yeah, that's right. And GL2C modulo unitary group is hyperbolic 3 space. And this adelic construction, what it gives is simply a disjoint union of actual nice honest manifolds, the ones that we saw before. But the advantage of this is that we've packaged the manifold. So I will want to know, I can pick out 2 of these connected components and ask, are they isospectral? But this whole package will be useful. Any questions?
What's C? Sorry.
So C, thank you. That's a good question. Okay, what is C? So first of all, these gammas, you can obtain them explicitly as follows. And what is C? C is, well, a priori is just the set of components of this disconnected manifold. But in fact, it can be essentially canonically identified with a certain class group. Or really a certain quotient of a certain array class group. So if you take, okay, if you want to know the details, if you apply the reduced norm map to this double quotient, you will essentially end up with something that will remind you of, if you've ever seen the definition of a class group using Adele's, you'll get a quotient of this. So the C is some sort of class group of the field over which we are working, and it parameterizes the connected components of this manifold. And this will be important. Any other questions? So let me just abbreviate each of these quotients, x modulo gamma g to yg. So that my manifold is a disjoint union of these yg's, and I will want to know are two of these isospectral. Isospectral for all I or whatever. Okay, a little bit more setup. So I'll just remind you, Hecke character is a continuous group homomorphism from this quotient. So you go from the Edels to C cross, but you demand that it be trivial on the global points. And again, don't worry about it too much because I can describe this to you very explicitly. So this, again, is a product of unit groups of completions, restricted product, but whatever. At the real places, so where the completion is the reals, every character looks like something like this. It's possibly a power of sign or not. So it's either sign times blah or no sign, and then absolute value to some power. So this is a character on R cross. And on C cross, instead of the sign, you take the argument to some power and the times the absolute value to some power. The reason I'm saying this is that I will refer to these Ks and Ss shortly, but you don't need to remember their role. Just remember it's something super explicit. You just write down actual functions from R cross to C cross, from C cross to C cross. Okay, so here is what our theorems look like, and there will be several of them. So at some point, I will give you explicit permissions for your eyes to glaze over. I just want you to get the general shape of these conditions. So take C1 and C2. So remember, these are going to correspond to two components, two actual manifolds in my disconnected adelic thing. Then at least one of the following two statements is true. Either there exists a quadratic extension of my field and the Hecke character with satisfying some conditions, or the two groups are representation equivalent. In other words, so let me pass over this terrain again. In order to prove that your two groups are representation equivalent, you're going to compute the groups of Hecke characters of a few finitely many specific quadratic extensions of F and check that there is no Hecke character satisfying certain explicit conditions. And I'm not expecting you to read the conditions, but I want you to see what shape they take. It basically says at real places, the parameters are restricted in such and such a way. In real places that split, in the real places that split in the quadratic extension, there is a restriction. For complex places, there is a restriction.
Exclusive or?
That's an excellent question. No, and that's the reason why I phrased it in this way. We think it's close to exclusive, but maybe I'll comment more on this. So the theorem only goes in one direction. It doesn't, you can prove representation equivalence this way by showing that there are no characters like this in any one of the finitely many quadratic extensions. On the nose, you cannot prove non-representation equivalence using this theorem.
You think those conditions are equivalent to some kind of cohomological vanishing or something.
I'll tell you exactly where these conditions come from. Hopefully, yeah. Any other questions? I'm loving those questions, by the way. Keep them coming. Okay. So that's one theorem. Here is another one. Again, take two connected components. Then at least one of the following two statements is true. The first one is the same, except that, everything is hiding in the small print. There will be different conditions now. And so if you exclude the existence of Hecke characters with certain conditions, you can conclude isospectrality of your manifolds. And the conditions, they look a little bit different. So the only reason they are on the board even to begin with is because I want to briefly look at them with you. So for example, let's go back. So here it says for every real place that extends to a complex place of the quadratic field, S is 0 and K is odd. And these are the parameters of the Hecke character. Here it says for every real place that extends to a complex place, vastly some extra conditions, S is 0 and K is plus or minus 1. So you see that this is a more stringent condition. There are a few negations going on here. So, if the manifolds are representation equivalent, then they are a fortiori isospectral. If you want to show that they are not it's harder to obstruct isospectrality than it is to obstruct representation equivalence. The upshot. And so, yeah, there is the hierarchy of these conditions. I'm not claiming that they're sharp, but the least you would want to check is that the hierarchy of these conditions matches the implications between the different isospectralities that you expect.
You actually have such isospectral manifolds that are not representation equivalent.
I love these questions. And give me 3 more slides. So far, there are no such examples, because the only condition that we knew to ensure isospectrality. Okay, and similar theorem for isospectrality for all I. At this point, I'm going to spare you conditions. And then there is one more that I do want to spell out. So either there exist Hecke characters with certain conditions, or for every I, the regulator quotient in degree I is rational. Okay, and I know what you're thinking. This is going to be, so first of all, Chiga-Müller doesn't give you this. So, I cannot recycle. You might think I'm cheating. I'm just using the conditions before, but Chiga-Müller doesn't tell you anything in each degree I by itself. And the conditions, here they are. But again, I'm not expecting you to read them. What I do want to say is these conditions are weaker than those for isospectrality. So it looks like it's easier for these regulator quotients to be rational than it is for the manifolds to be isospectral. And this should make sense to you because these regulators, they only see what's going on in homology. So basically harmonic forms, they only see Laplace eigenvalue 0. Whereas isospectrality means matching for all I. On the other hand, this is some fine Riemannian information here. These are some transcendental numbers. Okay, now are these and one more. We also have, so I asked, well, if these are rational numbers, then what primes appear? We have a theorem like this, prime by prime. So either there exists certain Hecke characters modulo p, certain mod p valued Hecke characters, or there is no p in the regulator quotient. But this actually relies, this is conditional on some widely believed conjectures about Galois representations attached to torsion classes of these manifolds. Not just that you can attach Galois representations to them, but that they have certain nice Descartes theoretic properties.
You use Chiga-Müller in this?
No, we don't use Chiga-Müller in any of this. So Chiga-Müller was just motivation, but it's logically completely unnecessary for us, which is a good thing because I don't know if there is a Chiga-Müller formula for orbifolds, for example.
But then how do you relate these regulators to the torsion classes?
Yeah.
Okay, okay.
Actually, I'm not sure I'll get to say much about this, so I'll tell you afterwards. Yeah, no, excellent question. Yeah. Any other questions? Okay. So are these conditions any good? Let me just show you a few examples. And I have to say, so we had, we spent, this took 6 years. And then about a month ago, Aurel, who's he has packages to compute with Hecker characters and so on. He has written a whole paper. This is a non-trivial algorithmic problem to classify all Hecker characters of a field, which he has solved. And so finally he implemented our conditions. 6 years was just the theoretical work. And the outcome of those implementations really surprised us. So let me show you a few examples. Here is a quartic field. It has 2 real places, two embeddings into the reals, and 1 pair of complex conjugate embeddings. Take the unique quaternion algebra ramified exactly at the 2 real places, at no finite places. It's a very explicit thing. It turns out you can compute that in this case, there are exactly 2 maximal orders up to conjugation. So the C, which you can just compute by computing a class group of a number field, is order 2. So take the 2 connected components that we saw before. So the only thing that we can ask in this setting is, are these 2 isospectral or not? And they turn out to be isospectral, meaning our conditions apply. So not just that they are isospectral, but they are isospectral because of one of the theorems that we had earlier. But they are not one isospectral. And so that such things should exist was expected, I believe, but you can find statements in the literature to the effect of this must be very hard to produce. Because there are examples of this in higher dimension. I believe this is the first 3-dimensional example. And this is also the first hyperbolic example. The hyperbolicity, I think experts here actually understand how these spectra work, which I don't expect that for hyperbolic manifolds or orbifolds in this case of any dimension, this is supposed to be very hard. And I haven't told you anything about how we prove non-isospectrality. Essentially, we use the same techniques. I haven't told you anything about the techniques yet, but we have to inspect everything, every step much more closely. I'll get to that on the last slide. I just want to say these orbifolds have volume 0.246. Okay, so what you say? Volumes of hyperbolic orbifolds are themselves an interesting kind of animal. There is a unique smallest one. I hope you can read it. It has volume 0.039. And then there is a unique second smallest one and third smallest one. And then there is an accumulation point. And that is roughly 0.309 something. And then there is a jump again, and there is a unique smallest orbifold of volume greater than this accumulation point, and then the story repeats. There is another accumulation point, and so on. This volume is below the first accumulation point. So, okay, well, if you prove this, you're welcome to say that Aurel and Alex conjectured this. Disprove it, then you're welcome to say that. Feel free to say that we asked the question. This might be the smallest pair of isospectral hyperbolic 3 orbifolds. So 2 comments. There are only finitely many hyperbolic 3 orbifolds of smaller volume, because this is and it's the first pair with this feature. It's below the first accumulation point. And one more comment. So I mentioned earlier that Voigt and Inowitz had an example of volume 2A24, which was the smallest they could find. I actually suspect that with Tsunada's method, you can probably beat this. But I'm not aware of anybody having tried to optimize Tsunada's method in this way. This volume is provably unbeatable by Tsunada. So Venera wins once and for all. And I haven't explained to you the construction of Sonata, but actually the construction is very simple to explain. And the proof of this claim is also very simple. So feel free to ask me after the talk. I can explain it to you in 2 minutes. Why Sonata will never beat this volume. Okay, another example. Were there any questions?
What's the strategy if you try to find smaller, like what kind of, what are you looking for?
Okay, so yeah, why am I umming and hamming about this being a conjecture? So I'm pretty sure that this is the smallest among all orbifolds that you get via this construction when you take maximal orders. But I had this KF, remember, which could have imposed, you're allowed to impose some level structure on your arithmetic groups. And Aurel is in the process of, but hasn't finished implementing, making the code sufficiently general to handle level structures. Now, typically, when you impose level structure, you will cause the volume to go up. But it could happen that with some higher level, we can find something over a smaller number field than we found so far. So I suspect that by the time we are ready to put this paper on the archive, we will probably be a bit braver because we will have eliminated level structures as well. It's, as I say, you'd have to get lucky for higher level to give you smaller orbifolds, but we can't exclude the possibility. Any other questions?
Do you expect accumulation points among these like volumes of things that which are isospectral?
I have probably not, but this you're definitely not allowed to say was a conjecture.
Okay.
Okay, another example. So here is another quartic field. It again has two real places, so one pair of complex embeddings. Again, take the unique quaternion algebra ramified exactly at the two real places. Again, there are exactly two conjugacy classes of maximal orders. So this class group is again has order 2. So take the corresponding orbifolds. Then these are hyperbolic 3 orbifolds that are isospectral for all I, but they are not representation equivalent. And once again, they are isospectral for all I because you can apply a criteria for representation equivalence. You actually have to prove it by hand. But this is actually easier than people already knew how to prove non-representation equivalence before us. I don't believe that people knew how to prove non-1 isospectrality before this. Actually, when I was telling Akshay Venkatesh about these results, the very first question he asked me was, how do you prove the negative part? And that requires some thought, which I haven't told you anything about. And these have volume 0.251, once again below the accumulation point. So again, there are only finely many hyperbolic orbifolds of smaller volumes. And still, even though it's a little bit bigger than the previous one, Sonata cannot beat this ever, provably. So perhaps this is the smallest pair of hyperbolic orbifolds that are isospectral for all I. And you know the rules. Okay, example 3, another quartic field. So these just happen to give us small examples, but you don't. And we want one complex place and two real places that are ramified in the algebra to get 3 manifolds. But the technique doesn't rely on this, so we can get manifolds of higher dimension this way. Just take other number fields with more real complex places, so other quaternion algebras. Once again, in this setting, there are exactly 2 connected components. So take those 2 and take these quotients. They are, I seem to have exhausted sort of things to slow. Wait, not isospectral. Okay, you don't look very impressed. You already knew how to produce not isospectral manifolds, fair enough. The quotient of regulators, though, in degree 1 is rational. Okay, you still shouldn't be too impressed because we know how to produce rational regulator quotients. Just take petty number 0, then these are determinants of empty matrices. Okay, but now feel free to be impressed if you want. So these have petty number 1. So the regulators themselves are, for all we know, transcendental numbers. This is expected by the general Kontsevich-Sergei philosophy. I don't think anybody can prove anything like this. But the quotient is rational. And again, we prove this using the criterion in one of the theorems. So these are not isospectral at all. They are not, well, I guess I only stated they are not 0 isospectral. They are nor are they 1 isospectral. They're just not isospectral in any degree. But this quotient of regulators is rational. And here is the same example, but with more colors. These are the fundamental domains of these two orbifolds. I didn't show you the pictures from the other two, because this is a slightly bigger pair. Well, it's quite a bit bigger. It has volume something. And who would have thought that turns out to be better for colorful pictures and talks? Because those small orbifolds, if you want to show, is to see the hyperbolic 3 sphere, you would have just seen a little colorful blob in the middle. Doesn't look so. Okay, so in the last 5 minutes, I will sketch some of the ideas that go into the proof, and this will hopefully answer many of the questions that were asked in the course of the talk. The big selling point of this adelic setup, the reason you want a disconnected manifold, even though you're just interested in 2 connected components, is that there is a Hecke algebra acting on, say, differential I-forms or homology or cohomology with any odd coefficients on this disconnected thing. And the way this works, so you don't need to know anything about Hecke algebra, so I'm just going to tell you explicitly what it looks like. For every prime ideal of the ring of integers of the field, you have an operator, TP, Hecke operator. And the nice thing about these connected components being indexed by some class group is that you can tell exactly which Hecke operators map forms on which component to forms on which other component. So if you take a component corresponding to an ideal class B, and then you take a Hecke operator TP, that will send that component to the component corresponding to the class of P times B. So in other words, in fancier words, this, let's say the space of differential I-forms is graded by the group C, and so is the algebra, so is the Hecke algebra, and this is a graded action. And this action preserves Laplace eigenvalues. And so if you could find a Hecke operator that sends your favorite component, first favorite component, to your second favorite component and acts invertibly, then we win. Not only have we then proven isospectrality, we've realized this is what actual spectral people who are not part of call transplantation. You actually get a linear map that just identifies the eigenvectors with each other. It doesn't just prove an equality of abstract sets of eigenvalues. It provides an explicit identification between the eigenvectors. So that would be nice, and you know where to look for them. You just have to look in the class. So you remember in these theorems, we had this C equals to C2 times C1 inverse. That's the graded piece of the algebra in which you're looking for these Hecke operators, because those are the ones that send the C1 component to the C2 component. So far, so good. Now, a priori, you know, this could just fail to happen. It could happen that for every Hecke operator in the right graded piece, it kills some line in this space of differential forms. And if that were possible, we would have no idea how to analyze the situation, how to, when this happens. So the main algebraic result, and this is buried in the technical part of the paper, but that's what is driving everything, is the following. It turns out that actually the only way you might fail to find such a Hecke operator is not if every one of them kills some line and they have nothing to do with each other, but there will necessarily be a single Hecke eigenspace in the space of differential I-forms killed by every TP that sends this component to that component. Okay. So they cannot use, yeah. Just pausing because this is important and it takes a second to process. And what this means, so think about this Hecke eigenspace. So Hecke eigenspace means it's a line that is preserved by all the Hecke operators, but we are saying, let's say you have two components, this group of components has order 2, then we are saying that every other Hecke operator has eigenvalue 0 on this Hecke eigenspace. And this should remind you of something. These Hecke eigenvalues, they if I call them AP, then this definitely reminds you of something. These are like the APs attached to an elliptic curve. Now, if you have an elliptic curve where all half of all APs are 0, then this curve has complex multiplication. And what this says is the Galois representation attached to the curve is induced from some quadratic extension, from a character of a quadratic extension. And this is mirrored on the automorphic side. So this is a sort of CM Hecke eigenspace, thing like this. And this is a theorem of Labesse-Langlands on the automorphic side that such CM Hecke eigenspaces, they come from automorphic representations of GL2 that are automorphic inductions. So automorphic induction is the automorphic side of simply induction of representations on the Galois side, from automorphic induction of a Hecke character. And so now we have a very strong restriction on when you might fail to find such an invertible Hecke operator. You need to have an automorphic representation of GL2. Well, really an automorphic representation of the quaternion algebra that transfers to the GL2 side, where on the GL2 side, it's an automorphic induction of a Hecke character. But we understand the automorphic representation theory of GL2 pretty well. So you can go through the classification of these things locally, at least everywhere, and match all these criteria. Okay, on the one hand, this has to come via Jacob-Langlands transfer from the quaternion algebra. On the other hand, it has to be an automorphic induction. And you can just run through the classification of representations of GL2R and GL2C, and you will find restrictions on these parameters, and they will be the restrictions that you saw in all these theorems. So yeah, you will get restrictions. I guess the point is you can, yeah, another important ingredient is Matsushima's formula, which basically tells you which automorphic representations appear in these spaces of differential forms. And then you can also apply it to, so if you want to apply it to homology, you just take Laplace eigenvalue 0. And then there is still the question, what do you do about regulators? Did you say anything about regulators? For some reason, I still have 5 minutes, so I'll try to answer it just in words. We set up a completely purely algebraic framework where you have a graded algebra, a graded module, and in that context, we define what is called a polarization, which is basically like a pairing with certain properties that mimic the properties that this harmonic forms pairing actually does have. And we define the notion of a regulator constant, which is supposed to mirror the definition of the regulator quotient. And we prove that, so, okay, suppose that you found a Hecke operator that sends the C1 component to the C2 component, acts invertibly on the ith homology. It has two additional properties that are very important. Firstly, it preserves the rational structure. So if you think of real homology, well, you can stick any coefficients in your homology. So you can define it as an operator on the rational vector spaces. It preserves the rational structure. And secondly, these Hecke operators are self-adjoint with respect to the pairing. And we proved purely algebraically that in such a situation, what you can do is, it turns out you can find another pairing that has all the same properties. It's non-degenerate and all your Hecke operators are self-adjoint and so on, but that takes values in Q on this rational structure. And this quotient of regulators with respect to the actual pairing that normal geometers use is going to be the same. It's going to be equal to the regulator quotient if instead you use this Q-valued pairing. And now this proves rationality of regulator quotients, because somehow it turns out this pairing is very important geometrically, but it turns out for the purpose of these regulator quotients, you could have taken any odd pairing that satisfies certain algebraic conditions, and you would get the same regulator quotient. So this is a formalism of regulator constants. This was pioneered by Tim and Vladimir Dokshitzer, originally for regulators of elliptic curves. But in a context where you had a finite group and manifolds, the analog here would have been the manifolds sit in a common finite covering, which is the case in Sonada's construction. But not here, so we had to completely revamp this formalism of regulator constants.